Jim, you're going to talk about cosmology, I guess, and kind of an extension of what you were talking about yesterday in the Saturday morning CMPS presentation.
Yes, sir.
So,
Actually, I have a few slides just on what I consider to be the essentials in crafting a cosmological model.
well, we talked about that before. You have some opinions about that, as I recall.
Exactly. And in fact, I had stated everything sort of in the negative, how to make an untenable model. And I think it was you that suggested it might be interesting to put that in the positive and talk about what are essentials that should be used rather than the negative approach, as it were. And so
Okay.
I prepared these slides partly in response to that.
Okay.
And I
Um,
realize I'm sort of a minority in this, in the sense that I work with full quantization, and that's a minority opinion, and I respect that. But I also um, respect the opinions of other people here, and we've got some great minds, and I'm always learning from what others have to say.
okay. Jim, a couple of comments. One is I'm not sure that we're going to have that we're that you're I'm not sure that we can spend 2 hours talking about your topic. What do you think?
I don't know. Well, I just have a few slides. It could be that I
All right.
just in the first
Anyway,
session, and
the reason I brought that up is because I do have some questions about the presentation from yesterday, and that got kind of messed up towards the question period.
yeah,
So,
what happened was something very strange, which I think all of us should be aware of. When I exited the StreamYard yesterday, the normal screen that I usually would get did not appear. That screen, probably everyone has seen, where it's sort of the ad for, it just goes back to the sort of the StreamYard homepage. Instead
right.
of that, I got a screen saying, stand by, we are uploading your recording.
Oh, yeah.
Now,
Yeah.
and that took about an hour. It said, don't leave this window until the recording is uploaded. And so I said, my God, maybe I was recording, and how could that have happened? I think it's a bug in StreamYard software. I thought about it a little bit more, and I realized that for the first time, I had shared screen using an application window, not the full screen. And I hypothesized that maybe there's a bug in StreamYard software that if you choose that particular option, in other words, you're just sharing a window of an application, in this case, my PowerPoint program, um, instead of the full screen, that there's a bug in StreamYard software which starts you recording. And so, therefore, when we got later on into the question and answers where there's more uh, um, bandwidth required to handle the different speakers and so forth, um, there was all of this breakup occurring, so that you might want to, those of you who might be sharing screen in the future, and you're sharing, say, your PowerPoint screen instead of the whole screen, that you might experience this bug as well. So I think my computer was slowed down by the fact that it was attempting to record. And so, and that involves a lot of disk writing. And as you know, that sometimes when when the system is attempting to allocate more disk space and writing out RAM to disk and so forth, there can be a pause in other applications, such as the live StreamYard talking. And I think that's what happened yesterday.
All right. Well, okay. It's kind of curious what you're talking about that this uh, it could be a lot of explanations, but basically, I've experienced this before many times, and so it's not a new occurrence. And I think what it means is you need to turn off your video streams when you have the question and answer session. That seems to be helpful because it went away when the third video stream went away. It seemed to work okay when there were only Ian and you, and then when a third person came on, it started going bad. Okay,
So
that's
when
my
you say,
reason.
Harry, when you say turn off your video screen, do um, you mean like turn off the camera for one's own self?
Correct. Correct.
Okay.
I that's the only thing that I mean. This is a problem that's occurred before. It's occurred with me quite a few times, and now it's happening more frequently with other people. I think it's just, you know, bandwidth limitations. All right. If you'd like to share your screen, we can get started.
Okay, doke. Let me do that. Let's see. Share, send request. Okay, I've got this. I sent the request. So I
Okay, you're ready to go.
share, and now I'm going to share the Microsoft PowerPoint window. Share sound. I guess I should click that and share. Okie doke. Do you see that slide?
Yes, essentials in crafting a cosmological model.
Okay,
Exclude failed ideas.
okay. Let's get going here. There's I have this sort of in two parts: things to exclude failed ideas, and things to include. And so let's start with some of the things to exclude. The theory that space and time are continuous with its miracles. Let's take as an example of this the various field theories out there, such as, for example, in gravity, we people will talk about in their use of continuity or continuous space and time model, the fact that there's a gravitational potential at every single point in space. Well, for any particular volume, there's an infinite number of points. Where is the miracle here? Well, in order for there to be in existence, in some kind of a physical existence, a potential, gravitational potential at every one of those infinite number of points, you're going to have some device at every single point, which is miraculous. It's going to have, I guess, sensors of some sort to sense the presence of material objects that are the source of this gravitational potential. It's going to have some kind of fantastic, incredible computational power to keep all of this incoming data updated to then give you this scalar value of what the potential is at that point, or a vector value even more complicated in terms of the gradient of such a potential, if you want to talk about that. So that's what I'm talking about here. The theory that
So
space...
you're objecting to field theory? Is that what you're saying? I'm not quite sure.
In the context of the model that space and time are continuous, yes. Binary mechanics does postulate electromagnetic fields, electric field and a magnetic field, which are the M and L type quanta, which I talked about yesterday. So I'm not rejecting the fact that there are fields. I'm rejecting how or what the physical mechanism is to determine what those fields are at an infinite number of points in any spatial volume. Okay, an additional thing. Additional spatial dimensions beyond 3D is, I think, a failed idea. For example, in the work in binary mechanics with just three spatial dimensions, we're able to accomplish quite a lot. So where do we have more than 3D? Well, perhaps the most common examples that everyone is aware of are special relativity and general relativity, where time is used, or they attempt to use time as a fourth spatial dimension. Most people, not everybody, okay, but most people believe that there's this thing we call the arrow of time. So that there's only one way that we can move in time. That's what the arrow of time is talking about, I believe. And so that when we attempt to use time as a as a fourth spatial dimension, what we're doing is it's sort of a crippled fourth spatial dimension because it can only move in one direction, whereas the ordinary spatial dimensions, X, Y, and Z, as we normally call them, in 3D space, uh, you can move either direction. And so that time is sort of a lame fourth dimension in those cases of special relativity. Other people, like our very own and much beloved Vladimir here, talk about a hypersphere of some sort as a fourth dimension. Notion of third point, notion that universe has a beginning time. I include this in my list. I realize that all of these points can be are discussable. So I'm not like laying down the law. I'm more or less making an agenda for discussion, if you will, because again, I respect the opinions of my colleagues here as some very, very extremely bright people. And anybody devoting their time to science has to be respected because, you know, most people are just doing frivolous things and seeking entertainment and whatever and doing nonsense. Whereas you guys here are actually spending real hours and time and sweat and to try to, in a very noble pursuit of knowledge. Now, this notion that the universe has a beginning time, I associate that, I would call that the biblical approach to cosmology. Like Genesis, you know, we have the time when everything started and God said this and God said that. And it all has a beginning. Of course, the Big Bang has this beginning time idea. So that I think that this notion just needs to be sort of set aside. And even I recall people like Cornelius, for example, saying in a past session, yeah, I mean, this is just something we can't even know at this point. We just don't have the knowledge or footing in order to really establish that such a thing as a beginning time of the universe. It's sort of a more a kindergarten view. I don't want to say that those who believe in the Bible are kindergartners, but you know, it's a little bit a childish way to look at things. Moving on, a fourth idea of things to exclude postulates, whether they're new particles, processes, or dimensions, which I covered above, which are really not falsifiable. For example, we've heard, just to relate it to things we have discussed previously here, again by our cherished, much beloved Vladimir, you know, that this fourth dimension of a hypersphere and so forth, which he himself says is basically not falsifiable. He doesn't use those words, so I'm not trying to put words in his mouth, which he did not say, but he did say that the curvature is so infinitesimal or so small that there's no way we can detect it. And so, again, this is something which I think puts a cosmological model, if it is included, in a tenuous position. So I think that's a failed postulates which can't be falsified are should be excluded, I believe. Next, exclude conservation laws which postulated events violate. We've heard a lot about the law of conservation of angular momentum as being something which is conserved in a cosmological model in these sessions. But this idea of things sort of exploding or extruding outward from a center violates that law, because whatever energy was in angular momentum, some of that is converted to linear momentum. That's how rockets get off the planet Earth. In order to get something up and away from the center, you've got to add some linear momentum. And if the energy was all in angular momentum, it means that some of that was converted to linear momentum, I would think. At least that's something to wonder about. Okay, let's move on to do not use unexplained measurements. For example, the speed of light, the electron charge E, Planck's constant H, etc., and others, like we've heard about the Rydberg constant, another unexplained measurement, wrongly called fundamental constants as input parameters. You're getting to pay dirt when you have none of these as input parameters, because they're unexplained measurements. And until those are accounted for, they can't be used as input parameters, else you've really passed the whole stage. It's like saying, I'm going to do calculus before I know how to do algebra. Explaining these measurements is like the algebra, but what people want to do is skip that explanation, skip that task, which is on the table for scientists to understand, and go straight to calculus. Well, it ain't going to work. And the fact that that does not work, I think, is borne out by the data. The fact that all of those theories, which use these unexplained measurements as input parameters, are failing. Take the Standard Model, for example. It uses a whole boatload of these unexplained measurements as input parameters, somewhere around 20 of them, 19 or 20 the last time I looked. Now, and yet the mainstream media is going to tell us that this is the quote unquote standard model. Standard meaning it's what everyone really accepts. But I can't find a single physicist that actually accepts the standard model. There are none. Everybody criticizes it and says it's inadequate and needs to be updated. So most physicists are on my side on this particular issue, I believe. Moving down the list, exclude assertions that physical principles are different at microscopic and macroscopic scales. All the macroscopic scale type data is simply statistical analysis of events which occur at a more microscopic level. I think this is the lesson that physics has taught us. And so where there are assertions that actually we have a new physical principle at some cosmological level, at a macroscopic scale, which doesn't occur at microscopic levels, I think that's a very questionable approach. And lastly, I think this is obvious, exclude logical contradictions among model components. Moving on, I sort of included this slide here as what you get when you fail to exclude the things that I just listed for you on the previous slide. So we could call this the side effects or adverse reactions. It's sort of like taking a medicine that has adverse reactions of conventional physics and cosmologies. There are contradictions, dualities, paradoxes, uncertainties, magic, miracles, Suspension of disbelief. Many questions are not allowed. Equation collapse, Planck limits, which is a magical mystery tour because those Planck limits are in fact just a combination of unexplained measurements. And so they too are in the unexplained category. As a matter of fact, to hit the ball out of the park, we might say if you're including unexplained measurements in your theory or model, basically your theory or model is just more unexplained stuff. Okay, let's move along here. I want to respect your time, so I'm going to move along fast here. What should we include? And of course, we want to include successful ideas. Yesterday, I argued that we want to start with the best toe, theory of everything available in crafting a cosmological model. This is absolutely essential. Now, there's one thing about the wording here. Think about theory of everything. If you have a theory or toe, which in fact is correct and complete, there can only be one, mathematically speaking. In other words, there are not a number of different toes. There's only one possible. Because if a particular one, in fact, accounts for quote unquote everything, well, there's nothing left to do as far as making a toe is concerned. And so that what we have is what I call many imposter theories of everything. And they claim to be theories of everything, but they're actually imposters. And if they use simple logic that I just presented to you, they would know that they're imposters. And so there's a certain amount of fraudulent activity there, in my opinion. I argued yesterday that binary mechanics explores consequences of full quantization of energy, space, and time with complete equations for system state and its time development. And whatever words we want to use to describe those equations, those are the equations which, in fact, run the binary mechanics simulator where various studies were conducted, as well as experiments using data that other people gathered, such as my lunar laser ranging analysis and so forth, which I think are useful and potentially very successful approaches. Third, on our successful ideas list, assert conservation laws which postulated events in fact confirm, such as the conservation of energy. In the example of binary mechanics, I'll let people with other theories speak for themselves, but in my case, the number of none of the time development equations changes the number of one state quanta. In other words, energy, which the one state quanta represent, is conserved. Next, use unexplained measurements only after derived from first principles. In other words, there's nothing wrong with using any of these unexplained measurements, which other people call the fundamental constants, and which are listed in Appendix A in almost every physics textbook you can buy on this earth. But really, the title of Appendix A should be Unexplained Measurements. These are the greatest body of mysteries in physics, and needs to be addressed before we can go on to a further development of our knowledge of physics. Much as I said before, you need to master arithmetic before you can master algebra. You need to master algebra, at least the basics of it, before you can master calculus and go on to matrix algebra and so forth. Assert that physical principles are the same at microscopic and macroscopic scales. This is sort of the inverse of what I was saying in the previous slide. And I'll just let that stand without any further comment. Include well-known and recently discovered phenomena. This is very, very important. For example, I read just the other day, and it was, I think, the day before, a previous presenter here, I think the person knows who he is, who was stating that photons do not interact to create particles, such as maybe electrons. It was a strange coincidence that just about the day before that presentation and that statement was made, a report came out where some guys, or and maybe some gals too, I don't know, at some well-known lab, were shooting laser beams at each other and causing them to intersect and getting electrons out of it. Now we can, as these reports become better known and discussed, it could be people find flaws in what those experiments are and maybe question that result. But here we have something which is entirely a finding which is entirely consistent with binary mechanics. There's no limit to quanta which are carrying electromagnetic radiation and the physical basis of it from combining in the electron bit cycles to reach the threshold for a creation of an electron. That's all right there in the equations of binary mechanics. There's nothing unusual about it. So it's very important, I think, to recently discovered phenomena, of course, can be questioned and must stand the test of time. Another well-known recent phenomena that's been ignored is the scattering data showing that the proton does not have a spherical shape. And how is this done? Well, if you use the Newtonian mechanic idea of billiard balls bouncing off each other and the angle of deflection when there's an impact between two billiard balls moving around on the billiard table, you get a particular distribution of angles. If the billiard balls are not spherical, or if one of the objects is not spherical in any way, this well-known distribution, what's called scattering distribution, there's a dramatic deviation from that. And that's the data on which is based the discovery, I think, not by me, but by some physicists out there at a well-known lab, that the proton does not have a spherical shape. Yet for that particular finding, I think, is well over 10 years old. And yet, even today, you can look and see that people are still modeling or are attempting to model the proton as a spherical object. So go figure that. Finally, the last item down below, a usable toe must be falsifiable. If binary mechanics or any other theory is to be used in crafting a cosmological model, there must be a way to falsify it. In the case of binary mechanics, it's rather easy. And I've tried to falsify it myself and failed every single time. And I've really put it to the test. Like I have talked about this crazy idea that due to the law of motion in binary mechanics, when we have full moon, the moon should be attracted to the Earth because the density of quanta between Earth and moon is greater during full moon as to when we only have a partial moon. And I used other people's data from observatories of lunar laser ranging, and I was going to prove that this inescapable conclusion of binary mechanics is completely false, and I failed. It turned out the postulate or the prediction of binary mechanics was in fact true. The moon was closer to Earth by some 10,000 kilometers during full moon compared to about 10 days away from full moon, when from the perspective of the Earth, the moon is of course darker, and therefore there'd be less radiation in a lower temperature. Lower temperature means less quanta being emitted from the moon's surface to fill the space and increase the density of quanta between Earth and Moon. Okay, so my last slide is just a quick summary of some of the major events in physics which have been won by binary mechanics as a theory of everything to use in making a cosmological model. First off, I've mentioned this already, I guess, is the century-long physics grand championship race, where we have the first ever derivation of basic constants from first principles. Every single one of the basic constants has been derived without using any of them as an input variable anywhere. Bit function defeats the wave function. Okay, in 20th century antiquated quantum mechanics, they use the wave function, and the best they can do is get probabilities of events, not actual exact values for events. So in the competition or event, you think of this like the Olympics, where you've got, various races and events in competitions. So in this particular event is the best system state representation. We include in binary mechanics both position and momentum. The wave function only can do one of those at a time. So the bit function defeats the wave function 2-to-1. It's really quite a win there. Best time development laws in that competition, the bit operations, which are the analog in binary mechanics to the operators in 20th century obsolete quantum mechanics, the bit operations defeat both QED and QCD. That QED is quantum electrodynamics and quantum chromodynamics, which deals with proton structure. And I've thrown a little bit of mud at that one already in this talk, so we'll leave it there. Best methodological advance in particle physics is bit function analysis. For those who've seen my talk yesterday, bit function analysis was used to discover, actually, because I didn't expect this. All I had was the equations and ran the program and then did some analysis of the results of that program, and found out that we could, at 0 Kelvin, that these equations were actually creating particles, 8 elementary particles, 4 matter particles, the 3 d quarks, which is down quarks, and the electron, and the corresponding 4 antimatter particles. And that was just an astounding result. Most parameters quantize. Well, space-time and energy quantization. Here we have a win there. There's no one who's attempting to quantize. Some people are taking little steps to say, well, let's quantize one of those 3 things and see how far we go. And but binary mechanics just dives in and say, let's just see let's just do the whole thing in one blow. Finally, and this is my last slide, by the way, for those of you who are already bored, the weak force debacle. Actually, there was a Nobel Prize given for the so-called unification of the weak force, and to review for some of you who may not be familiar, that involves those crazy things that are called the W plus and minus bosons and the Z boson. This weak force debacle was exposed by providing the best physical force mathematical definitions. If you want to see those definitions, they're in the time development equations of binary mechanics and summarized in table 5 in the paper on my website of Binary Mechanics Postulates. Finally,
okay, 3 minutes.
Okay, I'm almost done here. The best prediction of hadron particle structure and energy states. I added this one to my list because recently on the internet I saw that there was a couple of people who were very sad that they still can't pin down what hadron particle structure is. The proton, of course, is an example of a hadron particle. And so I was saying, my God, we have these people that can't even read. This was published years ago on the binary mechanic website. And yesterday I showed the hadron bit cycle, which has 42 locations. So that's 2 to the 42 spot cube hadron states are defined. So that's the summary then of my essentials in crafting a cosmological model. Things to look out for that should be excluded and things that hopefully you might consider including. Thanks for your attention, and I'll turn it back to Harry.
All right, Jim, thanks. Okay, we have about 2 minutes. I guess we're going to have a lot of questions about this. Your last slide was more not really that relating to cosmology, I think, but to particle physics, more or less. Would I be correct in saying that?
Yeah, you could say that. That's a fair statement. But if you're going, my premise that you have to start in making a cosmology with the best theory of everything available. And so this slide speaks to that point as to is binary mechanics, in fact, the best one?
Okay. Before you, let's say, I've got about a minute and a half. Okay. Now, the first thing I'd like for you to talk about when we come back is tell us what you really mean by theory of everything. I'm not really sure that's really, perhaps you've alluded to it. You might want to give us a kind of a definition of what you mean by that.
Thank you. That's a good idea. I'll do that.
When I hear that word theory of everything and I hear people talking about that, I just sort of like close my eyes and just kind of like, I'm not listening anymore because I just think it's an impossible idea. And, you're going to explain everything. I don't think that means you're explaining everything. I assume that it's limited to physics, not psychology and that sort of thing, or politics.
Yes, that's a fair statement, I believe.
Right. So I think we need to sort of have a clear definition of what that means.
And, okay, I'll start with that in the second session. Okay.
All right. I think we're going to be stopping here in 30 seconds or so. Does anybody else have any quick comments or anything they want? All right. Okay, as I suggested, could you tell us a little bit about what you conceive of as a theory of everything and what you think that means and consists of? And because I think it's kind of, even if you limit it to physics, it's kind of an all-encompassing thing. And
yes, basically theories of everything purport to, including binary mechanics, purport to explain every physical phenomenon. So the way you falsify a theory of everything is to bring forth a well-established, well-known physical phenomena, which is not accounted for by the basic assumptions and postulates, equations of a particular theory of everything. That's how you would falsify it. And I as I mentioned, I attempted to falsify binary mechanics right at the beginning, back in 2011, and failed. And every hypothesis that I've tested so far has confirmed that binary mechanics was making the correct predictions. So I haven't been able to falsify it yet. So,
let me interrupt here a little bit.
Sure.
So from your point of view, a theory of everything, as I see the current situation in physics, well, we have a contradiction. We have quantum mechanics and we have everything else, so to speak, classical mechanics, if you will. And quantum mechanics looks to be, it's not deterministic, it's indeterministic, while classical physics and the Newtonian conception is deterministic. So you have a big difference there um, in terms of, it looks like it's an irreconcilable difference. Um, Quantum mechanics looks to have required that you have an absolute rest frame, whereas classical physics claims there is no rest frame. And these are significant problems, and they haven't really resolved those difficulties. So a theory of everything should resolve these differences, I would assume. Correct?
Correct.
Okay, now I did notice that yesterday Nick sort of objected to the idea that there's an absolute rest frame, which seems to be one of the fundamental postulates of your theory of everything, binary mechanics. Correct?
Yes, without a theory, without an absolute reference frame, there's no way to determine whether a particle is in motion or not, except in that absolute reference frame. And in my experiments in the simulation of uh, cooling a simulated volume containing various energy quanta in it down to absolute 0 Kelvin, all particle motion stops. There's zero motion. And at that point, we can then state that we have particles in whatever is there in the ground state. And I was stunned to find, you see, I've been sort of led along by pursuing logical consequences of full quantization myself. And so, as a principal investigator in this, some of the slides that I showed you yesterday, I was sort of stunned and amazed that these things were actually occurring, such as the definition of the 8 elementary particles postulated in the spot cube model of space, and that was actually confirmed in such a dramatic way. In fact, Nick pointed out that I misspoke, saying that the incidence of these particular patterns corresponding to the 8 elementary particles was 20 times, not twice. I was saying twice. I misread the slide. It was actually 20 times greater than the random distribution. So that here we're actually talking about creation of things from what? From the equations. That's all there is, input.
Okay. Let me go back. I'm doing comments on your talk from yesterday, and I
Great.
guess we can the other comment I had was, this is kind of a presentation comment, and that was that you were talking about this gentleman Jerry, and I forgot his name, that you
James Hughes, the
James
MIT
Hughes.
student.
Yes, right.
James Hughes,
uh,
yes.
I Until you mentioned that, I was kind of mystified by where this binary mechanics came from and what the idea behind it was. And I
Uh-huh.
think that's a fundamental thing that you should actually start off by talking about that. And I suddenly then began to get an understanding of where you were coming from when you told that story. So I think that's an important piece of information. The
Well,
other thing is,
thank you for that point. I think you're absolutely right, because that gives some of the human color and what to the story, that actually the idea that, you see, in the continuous space-time model used in Dirac's quantum mechanics of the 20th century, I emphasize that because we're now, of course, in the 21st century. But in that model, where there's an infinite number of points, we have 8 different probabilities coming out from the 8 complex results of the matrix equation when you combine 2 Dirac equations, relativistic Dirac equations, with opposite handedness, which led to the definition or the prediction of the existence of the positron, which was then later discovered. Hughes showed that by rotating, now rotation of matrices is a very basic thing to computer programmers, and I've actually written programs to rotate matrices and so forth. Rotating matrices is a very basic thing that mathematicians and statisticians do. James Hughes showed me on the blackboard in my kitchen that if you rotate Dirac's 8 by 8 spinor matrix, what you get is the vertices of a cube. In other words,
right. Okay, now I
you
get
get 8 different locations.
right.
And so Hughes then
Here's
postulated, it's Hughes'
before we go on any further, could you bring back that slide? Can you bring up those basics? Okay, now
Yes, I can. In fact, the slides I showed today are in the same file that I can share my screen again and just bring up the slide that you want. Share. It's the exact same file. Oh, wait a minute. I've got to bring up this.
Okay, now one of the things I noticed is that your bit function has 3 bits, which means there's 8 combinations, right? I got that right?
Let's see. I didn't hear that because I was focusing on getting the screen shared. Say that again, please, sir.
You have 3 bits, and 2 to the 3 is 8. Is that not correct?
Well, there's actually 6 bits in the. Let's see. Let's just
all right. Show me the picture because
here's one spot. All of the 8 different spots here in the spot cube, each of those has 6 locations. There's 2 locations in each spot unit for the 2 different kinds of quanta. When I was quantizing the complex amplitude in 20th century quantum mechanics, which only gives you probabilities, as everybody knows, I did not want to discard information because this work in 20th century quantum mechanics was producing results.
All right, hold on a minute, Jim. There are 6 faces to the cube, right?
There's 6 faces to the cube, but there's 6 locations in the spot. Okay, so that's 2 to the 6 configurations of the electron spot, for example, that I'm pointing to right now with my cursor.
All right, that's a little bit advanced for most people. I kind of lost me there.
Well, that's 64 different locations, I believe, 2 to the 6th power.
Wow. Okay, so now we're into 64. We're into complexity very much in a hurry. I think most people get lost right at this point where you're talking about the spot cube, and now you just lost me because now you said there's 64 locations. And,
well, in the spot cube, there's even more.
Yeah, right.
Okay,
so this is kind of baffling, I think, to most people.
Well, all I can say about that is, we live in a very complex world. There's a lot of.
I'm just trying to make the comment. I'm just trying to make the comment that this probably needs a more explanation, because you talked about the spot cube, and then next thing you know, you're talking about bit cycles, and I was completely lost by the time. I didn't even understand what the spot cube was about. So my point is maybe some more emphasis on the basic spot cube and what you're talking about there. I mean, it's also confusing where you have X, Y, and Z axes, and the spot cube. It's kind of intimidating to really understand what you're talking about. That's my comment.
Well, okay. Someone else. I heard another voice there. Well, okay. Just think how complicated it is if you had an infinite number of points. Look at this volume here. This
All right,
L,
okay, Jim. Let me just stop you here. The other thing too is you got a lot of symmetries here, and I know more about symmetries than I know about the and so it seems to me like you have a whole bunch of symmetries that are related to each other, and I'm looking at these diagrams, and I'm trying to envision what the symmetries are, but you don't really talk about that too much. Do you understand what I'm saying?
yeah,
I,
well,
I think that's where the 64-bit business comes in, because you've got symmetries folded and mirror reflected on symmetries. Now, next thing you got 60. I mean, you got this single cube here, and now you're telling me there's 64 different combinations. I mean,
sure.
I'm like,
Like if
wow, that's really complicated already.
each one of these six locations that I'm pointing to here in the electron spot
Right,
can either be
right,
one or zero.
right,
So if that's true, then we have two to the six
right.
possible configurations for the electron. And you're saying, oh, that's complicated. Well,
Well, you
apparently,
just explained it. Now I understand it better.
well, thank you. But now let's go back to pre-binary mechanics where we have continuous space and time. How complicated is that? Because in this
Well,
volume, which is L is about 2/3 of a femtometer. That's the dimension here. And so we have a cube here for the electron, which is 2L cubed of volume. Now consider that in everyone else's view, there's an infinite number of points here that we have to worry about.
okay. Well,
So if you're talking about complexity, binary mechanics is simple dimple compared to, the kind of complexity that the people who are promoting continuous space and time are trying to foist on us. And no
okay.
wonder
Well,
nobody
in
ever
defense
gets
of
anywhere.
continuous space and time, I want to say that goes back to the basic um, mathematics and the development of mathematics. And then you have this guy Pythagoras who said that there's these things called irrational numbers, okay, which is a number that never ends in the calculation. And I'm going like, what the heck does that mean? Then you have transcendental numbers. Yeah, it's complicated because it's got this complicated, complex historical development. And physics just took that mathematical system and adopted it to because physics makes measurements using numbers. So if you're using numbers, you have to take over all that business about irrational numbers and rational numbers and transcendental numbers and all that mechanism of mathematics. Now I understand your point of view, okay, about this. So my point I'm making is it this is a system of numbers that comes from mathematics that physics adopted, and that could be the wrong system. Yes. Okay.
Well, what we're saying, basically what we're saying is that we're overturning the apple cart for all of those people who studied all that advanced mathematics all of those years. Because
Okay.
in binary mechanics, you only need three math ideas that even a 3-year-old has mastered, because these three ideas are intrinsic to being able to speak and understand a language. And that is the binary number, 1-digit binary number, yes or no, 1 or 0, up or down, right or left, full or empty, the binary choice. That's one. Second is the and function. If you look at the equations of binary mechanics, it's simply anding, performing an and function on different binary values to get a result. And lastly is the not function, where we convert a 1 to a 0 or a 0 to a 1. That's the not function. So those three math ideas that even a toddler knows, that can speak basic sentences, simple sentences. A 3-year-old is, I think, about the age level there. You have all the math that you need to understand 100% binary mechanics. All of the stuff about complex amplitude shown in this slide currently being displayed is just the origin of how all of this developed and where it came from with James Hughes' analysis of the spinor matrices of a pair of Dirac equations of opposite handedness that he showed when rotated actually gave you the coordinates of a cube, the coordinates of the vertices of a cube. Now, how could that be? So, in other words, these spinners, you see, when you rotate something, most physicists will agree with this statement. When you rotate a matrix, you haven't changed the physics, you just changed the point of view. So, when Hughes, these mysterious spinners with imaginary numbers in them, the I there in here that I'm pointing to with my cursor in the complex amplitude, these curious spinners turn out to be all real number vertices of a cube when this 8 by 8 matrix is properly rotated. So that which is the true physical interpretation, an 8 by 8 cube of space or these imaginary numbers? Hughes was saying it's the cube. And he postulated, not me, he postulated, I'm giving him credit. I don't have to. I could steal his ideas, but I don't want to steal anybody's ideas. Hughes said that he thought that space was actually a lattice of these cubes. My
lattice.
part,
Okay, lattice. All right, gotcha.
a lattice. That's correct. And so my part was simply to say, well, okay, James, if you're right, I couldn't find anything wrong with his matrix rotation. I've actually written computer programs to do that and could, if I wanted to, write the computer program to do the rotation that James Hughes did on my blackboard in my kitchen. But anyway, the next obvious question to me as a complete novice in all of this was to say, well, what is the size of these cubes? I mean, how big are they? Let's pursue this and see where we go. And so then I lost contact with James. He went his way in life, but I think he went to Africa, actually. Anyway, I then developed binary mechanics based upon full quantization of everything. I just said, let's just not quantize space. Let's just go the whole thing.
Okay, let me interrupt you here. So your view is that these cubes that James Hughes suggested are real. So that makes going back to philosophy, you're a realist as with respect to the existence of these cubes, quantized space cubes, correct?
Correct. Yeah.
Okay, so let's make that a little bit more specific. A realist philosopher of science says that these things that we're talking about actually exist. They're actual physically existent things. So for you, this lattice of space is a physically existent thing.
Yes.
Okay.
And in fact, the spot unit shown in the upper right in this slide is actually the most fundamental object that we can get to so far in our studies of physics. But actually, this object must contain mechanisms at a much lower level. So we're talking about tomorrow's physics beyond binary mechanics, where the various parts, where there must be mechanisms in here to implement the equations of binary mechanics, the time development equations, so that quantum move or don't move according to those equations, which are simply a combination of binary numbers, the three things I mentioned, and functions and not functions. Those equations, if you understand those three math ideas, by definition, you understand the equations of how the universe works. By the way, with those three math ideas, computer scientists accept that you can build a computer you can build a completely functional computer that does everything that, in fact, the computers that we're using right now use those three basic ideas. And those are the only three math ideas that you really need to build the laptop or computer that you're looking at right now. And so if you could build a computer with those three ideas, why can't you build a whole universe with them?
And that's what makes you, that's where your theory of everything is coming from. So you're saying, as based on your realist assumption about the existence of these cubic lattice and the um, binary equations that you're using, that's your theory of everything. The
Right.
rest of it is
I
just an
always
extension.
remain the skeptic, and I invite anybody to please bring a physical phenomena that's verifiable that is not accounted for by these 17 equations. If you can find any phenomenon.
Equations. Now you let the cat out of the bag. 17 equations. Wow. All right.
Well, the actual number of equations is sort of arbitrary. If we look at some of these here, um,
I'm just kind of being the devil's advocate a little bit. When you say 17, yeah, see, this is where it gets a little bit. Um, uh, I, for one thing, I can't really claim to be really knowledgeable about a lot of this physics that you're talking about, where you're talking about um, quarks and leptons and that sort of thing. That's kind of a little bit out of my ability to really quite understand it all. Um,
well, the time development laws here are
okay, yeah, now we're into an important thing: time development laws. So
okay.
we
See,
need.
the time development laws here. There's four bit operations, and they're applied sort of like a looping computer program. Like, for example, if you have a sticky key on your keyboard and you press it, and let's say you press the W key, and then in your word processor, the W is just repeating over and over and over again. And how do I stop this? And then you hit the escape key. Uh, that's an example in everyday experience that most of us have had of a sticking key on your keyboard that is looping uh, uh, over and over again. So that's what equation 17 at the bottom here is. That's the program of applying to the bit function, which is just the configuration of quanta in the volume, the four bit operations, scalar, unconditional, vector, and strong, these four bit operations to get a new state. And that is, so our universe is basically a looping computer program that is looping these four bit operations over and over again. And in fact, here's an interesting little um, uh, point of color, if you will, that if that program were to stop, because let's say whoever it is in charge of all of this needs to do some maintenance on the universe or whatever, and it's just stopped for a period of time and then starts up again, we'd have no way of knowing that, would we? We'd have absolutely no way to know.
Okay. Yeah.
So
I'm
how's
not
that for?
completely unfamiliar with this, what you're talking about here, because I had a friend of mine who, many years ago, he had a similar program, if you will, or a paradigm that he was working on, where he took the idea, your fundamental idea about the universe as a computer. And so I'm familiar with this idea, and he had worked on this for many years and had a lot of these ideas about everything was based on logical concepts, computer derived from computer science, and that's where you're coming from, as I understand it. So I can sort of understand that part of what you're saying. With respect to this particular slide, it starts with equation 7. Where are equations 1 to 6?
Those are the for
Okay.
any, for any physical theory. there are two things that you need, and only two. You don't need three or four or five, just two things.
Okay, so this
A
is kind of
definition of system state and a definition of the time development of that system state.
right. Okay, so these are all binary computer type equations. They're not normally we would think of as equation of motion would be m equals ma, and you'd get a
Right.
differential equation and use
That
calculus.
those are equations like of Newton, which are on the observational level. Those equations don't tell you how something moves, or they don't tell you why a certain element has a certain mass, or a certain object has a certain mass. They don't tell you that. Nor do they even tell you that there's an absolute frame of reference in order to quantify acceleration. So Newton was the beginning of step one in all physics, basically, which is to just describe the phenomena, observational, observational work, not what the mechanism of how the phenomena actually occurs. All right. Like, for example, I can describe a cockroach running across a table in terms of its position. If I have squares, a grid, or let's say the cockroach is running across a chessboard, so I can count the number of squares he crosses and so forth. That's observation. That doesn't tell me how the cockroach actually moves his legs. What that there's in fact a neural network in the cockroach to coordinate signals to the muscles, and there are contractile proteins which in fact can slide the filaments back and forth and in effect make the legs extend and move. That's where the mechanism of motion comes in. So Newton didn't even get close to that. He was talking about let's just describe what happens the best we can. And that was a very important step. I'm not minimizing that in any manner, shape, or form. But the next step is, well, then how do things move? All right. See, the biologists are not content with saying the cockroach runs across the chessboard, and I can actually photograph that with my video camera or my phone, and I can then look at the frames and tell you how fast he moved and so forth and so on. But no, in biology, the scientists working there are interested. Well, how does that sucker move? How do those legs move? See, so all I'm saying is maybe physicists should be as inquisitive as biologists are.
Well, I'm not going to argue with that point. Now, the next thing I want to bring up here is something that you touched on earlier, and that is if the a computer has a clock, okay, and every
Right.
time the clock sends a pulse out along the lines, the when the pulse arrives at the logic gates change their state. And so if the clock goes out, the computer stops. And of course, you pointed out earlier, you know, we wouldn't know if time stopped. So you don't really talk a lot about that in your. So could you tell us about what your idea is about how time, about time? Tell us about time. How does
Yes, it
time?
has to be what we would be, what the equivalent of what you mentioned, Harry, um, a master clock for the universe. And I don't have the answer as to what that would be. As a matter of fact, one can take everything that I presented, the equations and all the diagrams and analyses I've done, and actually do a Newton on that. What I just did to Newton, you can do to binary mechanics and say, well, Jim, all of that is just some observations. We still don't know how all of that works, what the mechanisms underlying what you've presented in those observations, how that works. So you see how science, so I see binary mechanics as a step in advancing physics as a science. Let's get down to actually our best appreciation of what the mechanisms are. And if you can show me any phenomena whatsoever that these equations do not account for, well, then we've got some real problems. Something is wrong or incorrect, either completely or partially, and needs to be adjusted in binary mechanics. And there are, even in these equations, for example, I pointed out there's certain things that are still not nailed down in my own mind. The bit operations order in the equation 17 here at the bottom of this slide, uh, I'm not certain that that is. There only could be one bit operation order which is correct, because we know from data that I presented yesterday and much other data that I have that these operations do not commute. That means, in mathematically speaking, that if you change the order of the operations on your system state, you get different results. So it's only possible that one of these bit orders is, in fact, the physically correct ones. But
Okay.
looking, yeah,
Let's say we got 5 minutes here. So let's go back to the original, to your first slides, if we could, and talk a little bit about the cubes, the ones with the cubes, the cube thing. Yeah.
here,
Okay. Now you were talking about, so in your theory, there's more than absolute space. You have absolute time, I think.
yes. In other words, I have a. By the way, I want to thank you here, Harry. It's a real privilege to be able to speak with such outstanding intellects as are found in this group. I'm really very blessed to be able to do so. So thank you. Now, what what I have assumed in the equation 17 that I showed a moment ago is that each of those 4-bit operations takes the same amount of time. That's purely an assumption that could be wrong. Okay.
Okay, but in your theory, there's the time unit is like the clock on a computer, and when the time unit when the computer gives the time pulse, then then the computer changes its state to another state, and the state that it's changed to is defined by the equations that you're talking about.
Yes. Now, I don't believe myself that in this vast universe that we have, it just inspires awe to even just see some of the photographs of galaxies and distant stars and so forth, that there's a sort of a central clock location, as is analogical to that of a computer, where there's a crystal there which is ticking, and that tick is detected and sent as a signal, as Harry just described, to run a computer, to synchronize everything in a computer's operation. I don't think that's what's going on here. Somehow, I think that at the local level, these processes, being binary processes, as I mentioned, just occur and are and at a particular rate, which is in fact the time constant, the primary time constant of binary mechanics, which is about 1 to the minus 25 seconds. And so so that is an area that needs for further study. And when one dives into binary mechanics, we're listing now a whole lot of things that are maybe assumed but possibly incorrect, that need to be checked. And anybody that makes a significant contribution in those directions is really at the cutting edge of physics as a science, in my opinion, and should be rewarded appropriately.
All right. Let's skip down to, let's proceed to the slides where you talk about different particle physics. Um, you had that, or you were talking about QED and QCD. Um, yeah, here we got the particle physics flux. Yeah, this is really kind of
Okay, here's the time constant that the clock is ticking at.
okay.
Okay,
So you have a discrete time. Time is advancing in discrete units according to your
that's right. Now, one way to falsify binary mechanics, this whole tree, would be to show that mathematically, I think this slide actually already shows that. But I'm not a trained mathematician, the PhD in mathematics from somewhere, so that if someone with those qualifications would chime in, I think that these three values here are a unique set of values and the only set of values which satisfy all of these equations to get what I call the secondary constants, such as Planck's constant, electric charge, E, and so forth. So that's the premise of this slide, that there is, in fact, only one possible way, that you can't change any of these values or come up with any other set of values. And you notice these are not the so-called Planck mass, length, and time, okay, which are purely fictional nonsense in my opinion. You can't change any one of these values, nor can you predict the value of any one of these values.
okay. So we were talking about this complicated. This my comment on this is a bit busy um, uh, for me to follow. I mean, there's a lot on here. There's a lot of stuff going on, a lot of interconnecting concepts. So that's a little bit. Um, it's this is all your charts are very daunting. They have way more information on them, I think, than a person who's uninitiated and not an expert in quantum binary mechanics to absorb. So that would be my comment on that. Um, okay, so Roger's now recording. Okay, do you want to continue on with what you were talking about, Jim?
I
Okay,
think
I'm unmuted. Yeah, what I was saying is that I think this is that these three values are the only possible solution that is consistent with the observed measurements for Planck's constant, for vacuum light speed, for elementary charge, E, and so forth. And that there is no other set of values which can simultaneously satisfy all of these equations. Another, and it's true that what Harry says is absolutely correct. There's more in this slide that this could be a whole hour presentation in and of itself. The one interesting thing that people are talking about is that actually bit velocity, the velocity that the quanta move, is actually pi times c. Okay, in other words, that's faster than light. So that all of this talk about, is there anything faster than light? Well, yes, there is. Or if there's not, you are challenging what this slide is saying. And if you can challenge it and show that there's anything wrong in this slide, please step forward. I'm not talking about right now today in this talk, but I'm talking about over time. I invite you, find something wrong with this. If there's something wrong, I would love to know.
well, how is pi involved exactly?
Well, this gets to the whole idea. If you look at the Speto model, there's no such thing as light transmitting in a straight line. As a matter of fact, particles don't move in a straight line either. They couldn't, could they? There are 6 faces to the spot cube, and the only way for a particle to move, as I made in a previous presentation, I think right here in Harry's Sunday sessions, they only can move through one of those 6 faces. They can't move in any arbitrary direction at that level, microscopic level of analysis, which means on the whole, they can't move in that actually light doesn't go in a straight line, nor do particles. Things go in many paths to arrive at the final destination. That's one good thing about Feynman. One of Feynman's ideas in quantum electrodynamics was that you had to sum all the possible paths of a quote unquote photon, which in binary mechanics is a collection of quanta, of one state quanta, all the possible paths that it can take in order to arrive at destination, at a destination from a particular source, okay?
Well, as far as why an object couldn't travel in a straight line, I'm guessing you mean it's something apart from gravitational influences. I don't quite understand why something couldn't travel in a straight line because
Well,
I mean,
Jerry, when you say gravitational influences, gravity is not considered to be a force in binary mechanics. It does not appear in any of the equations of binary mechanics. I discussed all of the phenomena which the gravity lovers have omit in terms of the creation of matter in my slides presented yesterday, on up to the creation of protons, up to the creation of atoms, including the entire periodic table, and then up to molecules. That's aggregation, okay? So I used the word aggregation because that word follows directly from the results obtained by applying the equations of binary mechanics, where matter is actually created as a consequence of of applying these equations. Gravity is a word that, like, if you want to go back in history. So if gravity is something current in your thinking, well, I guess maybe you're in some kind of a time warp. Maybe you're from the past. Because gravity, that's the thing of the past.
Well, would you say that binary mechanics explains the apparent force of gravity that we can observe, though? I mean, even if it's an illusion.
That's a fair statement, Jerry. Yes, that's a fair statement. You see, with binary mechanics, I get the best of both worlds. In analysis of data, I can look at collections of quanta and treat them as waves and do wave analysis of them if I want. And that would involve real numbers. That would involve continuous, an assumption, sort of a proxy assumption of continuous space and time. I can look at, even in the screen display of the binary mechanics simulator, you can look down on the right side column, and real numbers are used to tell you the position, which we might call in physics talk, the center of gravity of all of the quanta in proton bit cycles. And one can observe the movement of those of that position as protons move in the space. And so I get the best of both worlds. I can use the idea of continuous space-time and real numbers in my analysis of phenomena, but in terms of the theory of the origin of this phenomena, it's all binary, and only 3 binary math ideas are required, as I've stated, to understand it. So no one can
Well, I have quite a few questions that I copied and pasted from last sessions.
Great.
One of them is what exists in space when a cube is zero or empty, and what determines what exists when a cube when it is one or filled? How to account for the presence of different particles, waves, gravity, and so forth.
Well,
Maybe
let's
you've
take
already
one at a
explained
time.
this.
Whoa. Stop, stop, stop.
Oh, okay.
Please, one at a time, because I can't remember. I'm too old to
Oh,
remember
yeah. Oh,
five
that's cool.
questions. So what happens when everything is zero in a spot cube? That's called absolute volume. On one of my slides, if you look closely to the lower left, when the bit density or quanta density is zero, that is absolute vacuum in binary mechanics. However, I don't think you're going to have absolute vacuum anywhere for any length of time because there's always incoming quanta, all of this radiation running around all over the
Yeah.
universe that we talk about. Those are quanta. You say, well, what is this radiation? What is EM radiation? Well, it couldn't be anything but quanta. In binary mechanics, it couldn't be anything else. So you have the answer of what it is
Yeah.
right there. And those are always entering. And when they enter a volume with zero bit density or very low bit density, those quanta are going to be captured in the bit cycles of those spot cubes and spots.
Well,
So
uh,
there you go. So that's your answer to question one.
okay, thank you. Um, well, as far as the like, w- if a cube is empty though, well, I mean, how could a cube exist as empty? I mean, even if I mean, it would seem that there's always at least the very slight presence of electromagnetism or gravity or something. Is that factored in?
Well, well, if there's any electromagnetic effects, by definition, it's not empty. Okay.
Yeah.
The magnetic field is in fact the distribution of L bits. It's that simple.
Mhm.
And that is your magnetic field. Your electric field is the distribution of M type quanta or one states. So there you go there. Now, the if it's empty, and Jerry, this is a wonderful question. I'm glad you raised it because, by the way, all of your questions and comments are helping me refine my thinking, and I have to thank you a lot for that. The If it's empty, I'm postulating essentially that this spatial lattice that we're talking about is actually a set of physical objects. That the spot unit, for example, is a physical object that inside it must contain certain mechanisms that we can only imagine. Because how do these equations get realized in physical reality? We don't know the answer to that. I wrote one paper called Spot Unit Composition, and our composition of spot units, something like that, and I showed the results in one of the slides. I think one of the first ones, let's see if we motor on down here, we'll see it. There, this one. Of what parts are needed to implement the time evolution laws. Now, if these spot units are empty, as Jerry is asking about, the machinery still exists there, according to what binary mechanics is apparently saying. And I say apparently saying because with continuous space-time, you can almost say anything and get away with it. I mean, just look at all the theories of everything and all the conflicting theories out there. You can more or less say anything you want and get away with it. In binary mechanics, you can't do that. There's a certain scientific discipline. It must logically flow from what you already have. And in this case, if these spot units are empty, they contain no one states, and we're going to call that empty. Then we have, which by the way are neutrinos. Other people would call that components of a neutrino. That's what neutrinos are, the zero states.
Mhm.
But this machinery must continue to exist. If it didn't continue to exist, how could it capture incoming quanta and execute the laws of binary mechanics?
Yeah. Well, I have another question.
Okay,
Um, well, of course, there's a vast variety of different physical phenomena, various particles, waves, and so forth. If the cube is only filled or empty, how does it account for all these different types of elements and particles and so forth? I mean, is it determined by the surrounding cubes that correlate with each other, or how is that determined exactly?
well, in yesterday's talk, if you review it step by step, I would encourage you just to observe that each step builds upon the previous step in aggregating and in fact creating these particles out of thin air, if you will, and which then form protons and nucleons, which then form atoms, which include atomic numbers greater than one, up to 100 or so in our periodic table. And in fact, after that, very complex molecules, including those in our living beings ourselves. And it's a step by step aggregation process. And all of these aggregation steps, you might say that the word for gravity in binary mechanics is aggregation. All of these are simply ignored in Newton's and also Einstein's general relativity and Newton's universal relativity by just saying there's some mass there. And it's so simple as just to say there's so much mass and that's that.
Yeah. Well, as far as protons, that they aren't spherical. I mean, I personally don't know if they're spherical because I don't think we can directly observe them. However, though, if they had a rough size or shape, I mean, would binary mechanics suggest that it's pixelated? You know, that's like, you know, sort of like a computer image. When you zoom in, you can tell that it's tiny squares. Is it similar to that or something altogether different?
Exactly. Exactly. In other words, when you're, young and, the idea that space and time is a continuous thing seems to make a whole lot of sense because everything appears that way. If you look at your computer screen right now, you can see people moving and it looks like there must be continuous space and time, but really it's all pixels.
Wow.
That's exactly what binary mechanics is stating, or at least that's the hypothesis based upon the original inspiration of James Hughes, former MIT student, uh, started me off on.
Uh, would you say that the 3D cube grid or whatever it's called, would you say that it's stationary? Just in
Yes,
space?
yes.
Okay.
In other words, one of the inescapable conclusions, in my opinion, is that this latest of spot cubes is in fact an absolute
I'm feeling
reference
myself not
frame.
so good and have to leave the meeting. Sorry. See you next time.
Good to see it. Okay. Um,
Okay,
well, um, let's see. I have quite a few questions. Just some of them seem sort of outdated, not really relevant right now. uh,
not to worry. All these questions are good ones.
Meeting. Sorry.
I'd like to take this opportunity. We got like 20 minutes, I think. Um, does anybody want to go back to? We're sort of off the topic of cosmology, and I wanted to sort of bring us back to the three slides that you presented. So I guess if anybody has any more questions about the basic concepts, um, you know, maybe we could get those done with and then move on to commenting on Jim's 3 slides.
Sounds good to me.
So do we have any more questions about yesterday's presentation and the basic stuff? So I guess the next thing would be, does anybody want to comment on his presentation of today?
Well, I have some other questions, such
You
as
have other questions. All right. Could you put the 3 slides back up?
well, I must say my battery's getting low, so I might cut out in a second. But maybe it'll keep going. Uh, well, you had mentioned certain well-known and recently discovered phenomena that's been ignored. Like what specifically is that, and how would it apply in favor of binary mechanics?
One is the scattering data, which I mentioned, Jerry, where scattering results of protons hitting other protons reveal that at least the investigators claim that they reveal that the proton does not have a spherical shape. My work in binary mechanics right from the beginning showed that the proton does not have a spherical shape. And so that's what I would consider to be a well-known result, which is ignored. In terms of recently discovered phenomena, the so-called fractional charge, which is 1/3 of the elementary charge, which we see in quarks, and we also see in some recent experiments, again at leading institutions like Harvard, and I think this one's at Harvard, or maybe it's MIT. Well, there's a recent one from MIT again, showing, claiming to have observed fractional charge in electron transfers, and it's a very complicated sort of material science work where they're making measurements which imply to them or signify to them that in fact you can observe that the electrons are moving between the layers of their material a fractional charge at a time, which is exactly the mechanism of motion which I presented in a previous Sunday session for you all. And the videos are up on my site and other places as well. I edited those down to some videos on my site so that you can review those mechanisms of motion, which other investigators are now confirming. There also is a recent finding that was just a day or so before the statement in one of these Sunday sessions where Vlad was presenting that photons don't interact or cannot create electrons, where some people, I think this one was from Harvard, again, I don't remember exactly, but one can look it up, that that these investigators were aiming 2 lasers so that the 2 beams crossed each other, and alleging that electrons were being created, as it were, from this interaction of 2 streams of what I would call quanta. And
you mentioned this before.
Yes, and this is a very recent result, and people may, as in all experimental results, they go through a period of time where people can question the methodology, and really are the investigators' conclusion actually follow exactly from what they observed or not, and all of these debates which are necessary in science for science to progress. But that was a recent report which was published in a mainstream scientific journal, not one you have to pay for, okay, like the Journal of Physics Letters or whatever it was, and so, or Nature, and that's what that entry in my table of include well-known and recently discovered phenomena was referring to.
All right, let's talk about your first slide here. the first point you make, start with the best theory of everything available. Um, that's kind of my reaction to that is there such a thing as a TOE? And um, I think cosmology assumes that the best theory of everything available is general relativity.
Well, general relativity, of course, is excluded by my previous slide as to what things my own study in 2011 of lunar laser ranging is just one of many studies, as Ian Cohen has previously pointed out, that exclude general relativity. So general relativity, as far as I'm concerned, is off the table. It also violates another one of my rules, that if you look at the general relativity, I guess you call them field equations, um, C is an input parameter. Well, how can you use an unexplained measurement? Again, that's like trying to do calculus when you haven't mastered algebra yet.
Okay, I'd like to move
You're
on
sort of
to
doomed
your
to fail.
I'd like to move on to your third point. Assert conservation laws which postulated events confirm, such as conservation of energy. So my question is, and I'm not sure whether you've said this or not, does binary mechanics assert conservation laws?
Yes, it asserts that there is the conservation of energy because in none of
Hold
the
on,
equations,
hold on. Is that just an assumption on your part, or is that a theorem? An axiom is or a postulate is something that you assume to be true that goes into the mathematics. A theorem is something that you prove from the postulate. So is that a postulate or a theorem?
well, I'll let you decide on that one. But the equations, I don't, I'm not sure with postulate theorem or whatever, but the actual equations, time development equations of binary mechanics conserve the number of one state bits. There is no case of annihilation of one state bits anywhere or creation of them. So that's energy. Your one states represent energy. And so that we have the conservation of energy. Now, when I say that I'm very indebted to participating with other great minds here in these kinds of sessions, our wonderful Dennis Allen Jr., who is one of our CNPS participants that everybody I think knows, pointed out that there is a violation in the inertial propulsion phenomena of the conservation of angular momentum. And this was very educational to me because I said, wait a minute. I looked at my equations of binary mechanics, and there's nothing in them which prevents angular momentum from being converted to linear momentum or vice versa. In fact, the whole mechanism of motion, which I presented in a previous Sunday session right here, shows exactly that going on. So that people like Dennis Allen have helped me understand and better present what these equations are saying.
All right, let's move on to, that was a good answer. Use unexplained measurements. Okay, so now you're calling the constants of physics. They call these things constants. And uh, C, E, that would be the electron, H, Planck's constant, etc. Now, you made a statement that you derive these constants using binary mechanics. That kind of, that's probably not something that we could go into now. I'm sure you have a lot to say about that. But that certainly was interesting. The other comment that you made previously about this was that they're not a independent set in mathematics. They don't form a linearly independent set. So you've apparently looked at this issue pretty closely with binary mechanics. Would you give us?
What I did with the postulate of full quantization of space, time, and energy in binary mechanics. It's an inescapable now when I say the word inescapable, if some of you have a way to escape from this, tell me, but to me it's inescapable logic that if you're quantizing these three parameters, which are the units of measurement in physics, very basic things here, um, the to ask the question, well, what are the values that they have? And so what I did was a process of reverse engineering the equations or expressions for Planck's constant, speed of light, elementary charge, and so forth, to come up with these values. And as far as I know, these are the only possible values which satisfy all of these equations. So that the information dense slide that I showed you, the derivation of the constants that Harry said rightly is information intense. But if you look at that, you can say, is there any other set of values for mass in kilograms, length in meters, and the time in seconds that simultaneously fulfills or solves these equations presented? It's a purely mathematical problem. Now, maybe a mathematician who's better than me can actually prove that there is only one set of values. I'm claiming that the just simple logic tells me there could only be one set of values which satisfy all of these equations. But that's sort of an intuitive conclusion from a person who's not claiming to be a professional mathematician. I'd like a professional mathematician to chime in. Yeah, Jerry.
Yeah. Well, I have to speak into the camera again because I'm on my other computer, the old computer. But
it's working good.
Oh, good. Well, I think you mentioned earlier that the Planck scale isn't valid. Did you say that?
Yes, because those values are based upon unexplained measurements. So the Planck values are just more unexplained values because they're based upon unexplained values. Okay, that's simple logic. And by the way, they're inconsistent. They say the laws of physics would no longer apply below the Planck length. Okay. Well, what about the Planck mass, Jerry? The Planck mass is a huge value. Everybody accepts reasonable measurements for electron mass and proton mass in kilograms, and that's far below the Planck mass. So you see, there's no logical consistency in applying the Planck values for length, mass, and time, because in one case, they say if it's below the Planck length, then the laws of physics don't apply. But in the other case, if it's below the Planck mass, they don't say the laws of physics don't apply because everyone agrees that a proton mass is orders of magnitude less than the Planck mass. In other words, it's all a sinister fiction.
Well, as far as the Planck scale goes, I mean, I don't know if it was based specifically on something in particular or if it was just somewhat arbitrary, but I looked it up.
It's based upon these unexplained measurements, Jerry.
Okay.
Just look up on Google the Planck limits or the Planck constants, or the Planck lengths and so forth, and you'll see it's what I have called in previous slides and presentations a magical mystery tour, which is totally inconsistent because, as I've said, the proton mass is orders of magnitude less than the Planck mass, but they don't say that protons don't exist because of that.
James.
However, for a length less than the Planck length, they say that the laws of physics may not apply anymore. You see the inconsistency there?
Yeah.
In other words, let's be logical.
James, have you used this model to test other models? Because it seems like this model would be a good model to test other cosmological models and other models of physics.
Well, the binary mechanics simulator software is, at this time at least, is a free download. It won't be free forever. So go and get it while it's free, and do some tests. What we need is some minds like we see here today, asking penetrating questions. So we have a great selection of intellects here. What we need is some people like yourself, Rick, and others to say, well, by the way, the electric theory that you are a proponent of is included in binary mechanics, but binary mechanics would allege that it's not complete because it leaves out the unconditional bit operation and the strong bit operation. So,
well, you see, the electric universe theory doesn't go deep into the mechanics of how the atom works. That job has been taken over by Ito Cal, who again is I've showed Jerry the structured atomic model, SAM, and that job's been taken over by Ito Cal.
well,
The electric universe deals with basic workings of how the large structure of the universe works. It doesn't go into the detail of atomic theory or quantum mechanics or that. Other than to say Wallace states that there are smaller particles around the electron, like orbiting around the electron, doing their thing. Like,
well, that might be the one state quanta in binary mechanics is because for an electron you need three M-type quanta, as one of my slides showed in the bit function analysis.
right.
So that the quote unquote smaller particles would be quanta. You see, any phenomena that you're talking about, or anybody is talking about in physics, when you get down to it in binary mechanics, it must be made of quanta because that's the only thing available to make anything out of.
Right.
We got 4 minutes.
And when you're talking about creating electrons, I wasn't sure if you said that it can't be done by the photons. Did you? Am I correct?
Well, that's what if I understood correctly, that Vladimir, our beloved Vladimir, has said in a previous presentation. And quite interestingly, just within a day or so of that statement here on a Sunday, I saw on the internet this report that I cited, that people were directing two laser beams, presumably quite intense. I don't know.
Right, and that's the Brett Wheeler process that was
and creating
postulated.
electrons out of
That was postulated back in 1934 in by two physicists, and that was confirmed a year and a half ago or something like that.
Okay, wonderful.
Yeah, and they created an electron and positron pair from slamming two photons together.
Right. Okay.
And I think that process happens on the surface of the sun.
And as far as I know, binary mechanics is the only theory that can account for that phenomena.
Right.
Jim,
Move on to some of the other slides here.
I'm sorry. Oh, okay. I had a question then.
We only got 2 minutes.
Oh, okay. Well, can I ask a question? Okay. Well, Jim, how exactly was how was the binary mechanics like the discrete units as far as distance or increments of time? How is that arrived at? Because they have a specific measurement. I think you had said.
That's a simple answer, Jerry. I think we've already covered this. If you're going to quantize space, energy, and time, the next logical question is well, what values do they have? In kilograms, meters, and seconds. And to get so part two of the answer is once you apply that logic which says that they must have some particular values, you can start to reverse engineer. And this took me several years of work on and off of looking at all of these equations for the presented in my primary constants derivation slide, and to reverse engineer that to get the values that I presented.
Yeah.
Well, we're coming up on the end.
So in other words, you don't have to get a UFO that crash landed and start to look for the technology. Just the universe around us, the environment around us, is the advanced technology that we need to reverse engineer. And that's what binary mechanics is looking at.
I would be very much interested to hear how the reverse engineering was done.
Good talk, James. Good talk.
Oh, absolutely.
All right,
Well,
we're gonna
reverse
end here.
engineering was done by eliminating any contradiction in that slide of all of the equations, which is titled the physical constant derivation tree. Once you, wherever